So this is the second lesson on finding the nth term of a quadratic sequence. We're going to start off by recapping the previous lesson. So let's take a look at an example. We are going to find an expression for the nth term of this sequence. So let's remind ourselves of what a quadratic sequence is first of all by looking at the differences between the terms. So 8 to 25, we can see that there is a difference of 17. 25 to 50, we can see that there is a difference of 25. 50 to 83, there is a difference of 33. And 83 to 124, there is a difference of 41. So we can see that the first layer of differences are different, and that instantly tells us that this is not a linear sequence. So let's now look at the second layer of differences. 17 to 25 is a difference of 8. 25 to 33, 8, 33 to 41, also 8. So we've identified the differences between the first differences. Now the fact that the second differences are the same tells us that this is a quadratic sequence. And last lesson we then found the nth term of such sequences. How did we go about doing it? Well, we know that the general form of the nth term of a quadratic sequence takes the format Tn, where Tn is the nth term, a multiplied by n squared plus b multiplied by n plus c, where a, b and c have to be found. Now, how do we go about finding a, b and c? Well, there are a series of rules that we can use following the method that we learnt last time round, starting with a, which is equal to half of the second differences, which are all the same. So in this case, a is equal to half of this number here, which is the same all the way along, so a is equal to 4. So we know that our nth term formula will start off 4n squared. And then of course we're left with having to find b and c afterwards. So finding b and c, I've set up a table which shows the terms of the sequence 8, 25, 50, 83, 124 and their position in the sequence, i.e. their n value. So 8 is the first term, 25 is the second term, and you can see the n values listed above. Now, because the formula for our nth term contains 4n squared as a starting point, the next row will calculate the value of 4 times n squared. Remember that our rules of BIDMAS apply here, order of operations. We need to square n before we multiply by 4. So this will give us a layer of values which are 4, 16, 36, 64 and 100. Now the next row is going to be Tn take away 4n squared. So each of the Tn values subtract the value of 4n squared below it. So this gives me 4, 9, 14, 19 and 24. And we can see here very clearly that we have a linear sequence here in this part of the table. Now, finding a nth term for just this portion here, which I'll highlight in blue, is easy. We can see that the differences are 5, so that must mean we have 5n. Now, 5 times 1 gives me 5, but I want to convert it to 4. 5 times 2 will give me 10, but I want to convert to 9. 5 times 3 will give me 15, and you can see in each case it's 5n minus 1, which gives us the formula for this part here. So the overall nth term puts together all of these pieces, and it is 4n squared plus 5n minus 1. So we combine this piece here of the jigsaw and this piece here as well. And you did several examples of this in the last lesson. We're now going to look at a second method for finding the nth term of a quadratic sequence. Some people like to call this the A, B, C method. And we're going to look at how this method works. Then we're going to do a second example just to really consolidate how to apply the method. And then afterwards we will look at why the method works. So here is the same quadratic sequence that you've seen previously. And here is how the method is going to work. I start with highlighting this value here, and I write down that it is equal to A plus B plus C. Now, let's remind ourselves what A, B and C are. They come from the idea that the nth term takes the format an squared plus bn plus c, which is a quadratic format. Quadratic because, of course, there is an n squared term as the highest power. So a plus b plus c is equal to 8, which is the first term. Now, let's find our first layer of differences again. We wrote them down last time. They were 17, 25, 33, 41. We then take this first difference here and we write down that this is equal to 3a plus b. And we'll learn why that is a little bit later on. We then build up the next layer of differences, so 8, 8 and 8, and we write down a third equation because these values here, which are all the same, are equal to 2a. So we now have a system of 3 mini equations to solve. We have 2a equals 8, the easiest one, 3a plus b equals 17, which we can solve once we know the value of a, and finally a plus b plus c equals 8, which we can solve once we know the value of a and b. We can find c. So very, very simply, the first little equation gives us a equals 4. The second equation then gives us 12 plus b equals 17, so b is equal to 5. And the third little equation then gives us 4 plus 5 plus c equals 8, which then easily allows us to work out that c equals minus 1. Remember that the nth term takes the format an squared plus bn plus c. So we can now say that the formula for the nth term is 4n squared, using our value of a, plus 5n, using our value of b, minus c. And it's exactly the same result that we got last time. Let's try this with another example. So here is my sequence. It's a different one. I'm going to fill in the first layer of differences very carefully, as you can see. And I'm going to fill in the second layer of differences as well. And again, we can see that the first differences are different, but the second differences are the same. So we have a quadratic sequence. Now, let's think about those 3 rules we wrote down last time. The first term is a plus b plus c. The first difference between the first and second terms is equal to 3a plus b. And the first of the second differences, well actually all of the second differences are the same, is equal to 2a. So let's solve this system of mini equations. We have 2a equals 4, which tells me straight away that a equals 2. I then, from the blue result, have 3a plus b equals 9. And I now know that a equals 2, so I know that 6 plus b, be careful here because we have a 6, a b and a 9, and it's easy to make mistakes in the presentation of the algebra of these. So b is equal to 3. And then I have a third result, which is a plus b plus c is equal to 1 up at the top in red. So a is 2, b is 3, plus c must equal 1. And this is super simple to solve. C is equal to negative 4. So I can tie together all of these pieces of information, which give me my final result that the nth term is equal to 2n squared plus 3n minus 4. Now, do I know this method works? Well, we can check. Let's choose an n value. So this term here corresponds to n equals 3. It's the third term. So n equals 3. Let's use our formula to evaluate the third term and then check that it actually equals 23, the actual third term. So 2 multiplied by 3 squared, I'm subbing into this, plus 3 times 3 minus 4. Let's simplify this. So this is 18 plus 9 minus 4, which is the same as 18 add 5, which is 23, which is the third term. So it does appear to work using a quick check. So now we're going to try and understand why this method works. Where do these three little equations come from? So I've got the same example we looked at previously written out again, the terms of the sequence Tn and the corresponding n value of each term. I've also written out the first layer of differences and the second layer of differences as well. Let's remind ourselves about the nth term. The formula for the nth term is going to be a quadratic result, which means that its highest power is a square. So an squared plus bn plus c. Now, what happens if I substitute n equals 1 into this formula here? This gives me t1. And I can input n equals 1 into the right-hand side of this. It's a times 1 squared plus b times 1 plus c, which tells me that the first term of the sequence is a plus b plus c. But that's what we said before. Remember, we said that the first term of the sequence was a plus b plus c. So that's why. That's where the a plus b plus c actually comes from. Now, the second rule, if you remember carefully, was that we said this difference here, i.e. the difference between term 1 and term 2, was equal to 3a plus b. But where does that actually come from? Well, we know that this result is a formula for the first term. So let's input n equals 2 to find a general result for the second term. So this would be t2, and what I'm going to do is I'm going to take this formula here and I'm going to replace n by 2. So that is a multiplied by 2 squared plus b multiplied by 2 plus c, which tells me that t2 is equal to 4a plus 2b plus c, and that is a result that represents the second term. Now, if I want to actually find the difference between the first and second term, so difference between t2 and t1, well then I have to do a subtraction. I have to take t2 and I have to subtract from it t1. Let's write that out. So that's 4a plus 2b plus c, subtract a plus b plus c. Let's do the subtraction. That gives me 3a plus b, which we've seen before, haven't we? So the difference between term 1 and term 2 is equal to 3a plus b, which is why we can make this difference here, the difference between the first term here and the second term here, equal to 3a plus b. Now, there was a third rule, if you recall. The third rule took this difference here and said it was equal to 2a, i.e. the second differences of the quadratic sequence are equal to 2a because they're all the same. Now, how can we find out this result algebraically? Well, to find out the second difference of the sequence, we need to know this first difference here, which is the difference between the second and the third term, which means we need to know the third term. We already know that the first term is t1, which is a plus b plus c, and we know that the second term is T2, which is 4a plus 2b plus c. So let's find the third term. So we need to substitute n equals 3 into our formula for Tn. So we're used to doing this now. N equals 3 gives us T3 equals 9a plus 3b plus c. And that's the third term. So if I want to now find the difference between the third term and the second term, i.e. this value 25, this is where this value 25 comes from, I can do a subtraction. So the difference between T3 and T2 is equal to T3, which we've just worked out is 9a plus 3b plus c, subtract T2, which we worked out as 4a plus 2b plus c. Let's do the subtraction, and it comes to 5a plus b. So this term here, or this difference here, I should say, is 5a plus b. So how do we then get the second differences, the layer of second differences? Well, we find the difference between the differences. So the difference that we are looking at is 5a plus b. You can see it here. I'll just highlight it again in a circle like that. And we're going to subtract from it the difference that comes before it, like that, 3a plus b. Let's do the subtraction, and we're left with the second difference of 2a. So we can see that that's where this result, 2a equals 8, comes from, algebraically. So if you're going to use this method to find the nth term of a quadratic sequence, you are going to need to learn that the nth term will take the form an squared plus bn plus c, and you're going to need to learn the rules that a plus b plus c is equal to the first term of the sequence. A plus b plus c equals the first term, so this 8 over here in this example. You're then going to need to learn that 3a plus b is equal to the second term minus the first term. So that result corresponds to this value here in the example that we did previously. And the last rule that you're going to have to learn is that 2a is equal to this value here, which is the second difference. And of course, the second difference is the same throughout your quadratic sequence. Now, if you can memorize those 3 rules, you can use this method. It doesn't matter which method you use if your aim is to try and find the nth term of a quadratic sequence. What is crucial is that you can use the method accurately, that you can use the method efficiently, and that you understand why the methods actually work in finding the nth terms.